Hey, for my project, I'm going to analyze the speeds of three types of tennis serves and the physics behind the swing. Let's find out how spin affects the velocity and how the racket's impact angle plays into crafting each type of serve. Let's begin with the first type of serve, the flat serve. It is regarded as the fastest variant due to the direct transfer of power to the ball. Stop right there. Analyzing the racket, we can see that the racket face is oriented straight ahead due to pronation, allowing the full transfer of kinetic energy into the forward direction. The ball traveled 18.3 meters in 0.46 seconds. Since velocity is distance over time, we calculate a velocity of 39.8 meters per second, or approximately 90 miles per hour. Our second type, the slice serve, is considered the general-purpose serve, and although not quite as fast, it adds sideways spin on the ball.
Very good.
Halt! The contact angle of the racket is angled this time. This is to impart a spin on the ball to help it curve in. This one was slower, with 16.5 meters traveled in 0.48 seconds. We calculate a velocity of 34.4 meters per second, or 77 miles per hour. The kick serve is the third and final type of standard serve. It contacts the ball while brushing the racket up, creating topspin on the ball, allowing for a higher bounce. It is the slowest of the three. Here, the racket brushes upward to create topspin, allowing for the best control and bounce. Perfect if you're short or enjoy rage baiting your opponent. The kick serve traveled 17 meters in 0.66 seconds, a velocity of 25.8 meters per second or 58 miles per hour. It may be slow, but the placement and bounce make it a pain for any opponent to return. Different tennis serves are created by changing the angle of racket contact with the ball, which changes how energy is distributed between forward motion and spin. For the flat serve, the racket contacts almost directly through the center of the ball. This minimizes torque and produces very little spin, so most of the energy becomes forward velocity. Using video analysis and the equation v equals d over t, or our velocity equals distance over time equation, I calculated my flat serve at approximately 90 miles per hour, making it the fastest serve because nearly all the racket's energy is transferred into translational kinetic energy. For the slice serve, the racket brushes across the outside of the ball, creating side spin. This produces torque and angular acceleration on the ball, with the equations torque equals inertia, angular acceleration. My slice serve traveled around 77 miles per hour. Although it was slower than the flat serve, the added side spin created a sideways Magnus force that curved the ball through the air and changed the bounce direction after landing. And finally, for the kick serve, the racket moves upward behind the ball at an even steeper angle, creating heavy topspin. My kick serve traveled approximately 58 miles per hour. In this case, much more energy was transferred into the rotational motion instead of forward speed. The topspin produced a downward Magnus force, allowing the ball to clear the net safely while still dropping sharply into the service box. The ball's kinetic energy can be modeled by kinetic energy equals 1/2 mv squared. And since velocity is squared in this equation, the 90 mile per hour flat serve contains significantly more translational kinetic energy than the 77 mile per hour slice serve or the 58 mile per hour kick serve. Overall, the physics shows that increasing racket contact angle decreases the spin speed, but increases control, curvature, and bounce, and your ability to rage bait your opponent. The aforementioned Magnus force is the aerodynamic force created by a spinning ball as it moves through the air. In tennis, either topspin or downspin. As the ball spins, it changes airflow speed, creating a pressure difference, allowing it to curve. We used this curve to curve the ball sideways in the slice serve and downward for the kick serve.